welcome to the 69th session of the Porous Media Titan Talks. We are part of the Interpol Young Academy, and we aim to bring early career researcher, PhDs and postdocs the opportunity to present their research to the worldwide Porous Media community. I'm Sarah. I'm a postdoc at Evaporation University in Edinburgh, and I'm joined in the studio today by Madi Mansouri from the CNRS in France. And today for this session, we have the pleasure to host Rosalie Krasnoff from the University of Columbia and David Rieder from Eindhoven University of Technology. So please join us in welcoming them. Feel free to engage anytime in the discussion by writing your question in the YouTube chat. And I want to remind everyone, if you're not familiar with YouTube, that you may need to log in with a Google account, to leave comments. So please check if you can already welcome our speakers, and we will have Q&A at the end of each talk. Without further ado, I will introduce our first speaker today, Rosalie Krasnoff. She did her undergraduate studies in environmental engineering at Cornell University, graduating in 2020. She is currently a PhD candidate in Professor Shaina Kelly's group in the Department of Earth and Environmental Engineering at Columbia University. Rosalie is studying the influence of transport phenomena on precipitation action in porous media, focusing on carbon mineralization applications. She also explores how the modifications of the microstructure of cement can increase the formation of strengthening carbonate minerals during CO2 clearing. And today, our talk will discuss some microfluidic developments, approaches and challenges of induced crystallization in microfluidic experiments. So, Rosalie, thanks for being with us today and agreeing to present your work, and the floor is yours.
Amazing. All right. If I pop my slides open,
yeah,
we see them. All right.
Yeah.
Okay. Perfect.
Ready to start.
Great. Thanks for the introduction. Good morning to anyone who's in the States. Good afternoon to those in other parts of the world. I'm going to talk to you today about my work for my PhD with Professor Shaina Kelly. This talk is entitled Microfluidic Investigation of Cooling-Induced Nucleation and Crystallization Behavior in Porous Media. So the motivation of this work is just that we want to understand some of the transport controls on crystallization. So what some members of my group work on, and also what I work on in other projects, is the application of carbon mineralization, where we have ions dissolving from a rock interacting with the CO2 that's dissolved into aqueous form, precipitating carbonate minerals in either a rock, or I also work on cement, so some porous media. This work is relevant maybe to those applications and also to perhaps more engineered systems, so like separations, which we typically think of doing that in a bulk solution, but perhaps if we're looking towards using filters or even doing separations in soils where we're trying to immobilize certain ions, precipitate them within a porous media, this work could be useful. And then there are also scenarios where precipitation is not desired with membranes or other porous structures that you're using that you want to keep clean, where precipitation would be fouling those materials. And thinking about various pore scale crystallization behavior drivers, we talk about the morphology of the pore space, just the geometry of the pores and how things move through them, as well as the partial saturation state. So those fluids that are interacting, providing the ions that then are going to precipitate. How do they sit in the pore space, which is the wetting fluid? How much of each fluid do we have? And then a competition, or sort of process that's influenced by both advection and diffusion. So for this experiment I'm going to talk about today, we have both diffusion and advection in certain parts of the experiment, as well as a reaction term, where when we have precipitation, that's a sink for the ion. And because this is temperature-driven, a temperature-driven process, we also want to think about transport of temperature and heat as it moves through the system. And so, just stating my objective, to investigate the influence of transport phenomena on supersaturation and thus crystallization in porous media, investigated on realistic laboratory timescales where we can actually see this under the microscope, versus waiting what can sometimes be years to see reactions, maybe even longer than a PhD sometimes. So we have a bunch of different ways to drive supersaturation, which is what's necessary to induce crystallization. I'm going to talk about, we've sort of, in my work, I've looked at a bunch of these. I'm going to focus on one today, but moving from right to left here, in a carbonate, forming carbonates is complex because we have ions being sourced. So in this case, this is a reaction I did with MgO grains. So you can sort of see the remnants of these grains that were donating the magnesium to the reaction, and then CO2 was dissolving from supercritical form, or in other cases could be from a gas form, into the fluid in the pore space, and then reacting to form, in this case, nesquihonite formed, so these sort of darker needle-like structures that began to fill the pore space. We have ion sourcing from a bunch of different places. There's a lot going on, so we have the sort of coupled complex system of various dissolution rates influencing our overall supersaturation. There's also evaporation, which I haven't worked on too much, and I think we're going to hear about more later, but that's another way to drive crystallization. And then what I'm going to talk about today is a temperature-dependent supersaturation. So copper sulfate is, I think, a better zoomed in over here. It has the solubility of copper sulfate is very temperature dependent, and so we can at a high temperature create a solution that is undersaturated by dissolving quite a bit of this material, and then as it cools it becomes supersaturated and begins to crystallize out. And so that is the way we're able to induce crystallization in this work. And I guess they have the sort of another reason we chose this mineral, which I'm calling a proxy in this case. It's not necessarily that we're exactly interested in copper sulfate specifically, but crystallization in general. They have these beautiful blue crystals that are fun to look at and also easier to visualize, which is an added benefit for this work. And then the microfluidic device that I use is pictured here. So we start by 3D printing this larger cell that has inlet and outlet ports that we connect tubing to. And then in the middle, we have a little well that's 7 by 7 millimeters, and that is filled with soda lime glass beads. And so we get this bead pack matrix in the middle to study crystallization, and it has a little bit of depth, and so this is a 3D microfluidic. We were interested in seeing 3D flow patterns, not just 2D, in order to sort of reflect the reality of a 3D matrix a little more accurately. Obviously, if you've worked with microfluidics, this also comes with visualization challenges because we can't necessarily see exactly what's happening all the way through. So there are, trade-offs with every design, and that's I'll get into some of the ways we imaged those in a second. So just to walk you through my experimental setup, we've got the microfluidic device under our stereoscope using a syringe pump to inject hot fluid that was initially undersaturated, and that cools to ambient temperature. We actually also have a syringe heater, so this, in later versions, this is wrapped in a tube that keeps it warm. And the experiments follow 2 stages. So in the first stage, I inject the fluid in. We have forced imbibition at varying initial flow rates. And then this is followed after a couple pore volumes have gone through the chip. We follow this with shut-in. So sort of it reaches steady state, and then we enter a diffusive regime where there's no more advective flow, and capture images for 90 minutes with our stereoscope in order to see precipitation dynamics on lab timescales. And the data that we collect looks something like this. So this is 30 minutes of an experiment I did where you can see these crystals starting to grow, just sort of darker, more dense regions, and they come through slowly, but you can usually see interfaces, the very edges of the crystals, and then we image the end state with micro CT and are able to look at those beautiful bright crystals in 3-dimensional space with our micro CT. And then I extract those crystal surfaces and look at where they sit in the pore space. So this is sort of isosurfaces extracted into a little 3D image. And one way I look at them a bunch that I'll show throughout the presentation is just a 2D top-down view. So we're looking at them sort of a sum over the z direction, and the more yellow or green colors represent more pixels in the z dimension being crystal, but this allows us to see the distribution of the crystals over that sort of 2D top-down view. All right, now getting into actually what's going on here. So we know that thermodynamically larger crystals with a lower surface area to volume are generally favored. And kind of another way to say that, or what that means, is that precipitation is preferred on existing secondary crystal surfaces versus creating an entirely new crystal. So this data is from an experiment that's actually not done under the stereoscope, but instead entirely done in the medical CT, our micro CT scanner. And so we see change about every 3 minutes. I took a scan and we can see the change in crystals over time. So in blue, that's the number of discrete crystals. So that increases very rapidly over this initial period, and then pretty quickly, around 20 minutes in, levels off, and it looks like it actually decreases. That's because some of the crystals grow into each other and begin to count as one, but it's not actual dissolution, and we can see that in orange with the total volume of precipitated copper sulfate. That's increasing steadily over this period. So although there's still more crystal to precipitate, and it's continuing to precipitate in this second regime, we know that the number of objects is actually not increasing. And so just a visualization of this graph on the right, we can see a comparison of the isosurfaces of the crystals at 2 different times, 16 minutes and then about 20-something minutes later, and just flipping back and forth. For the most part, you can see existing crystals are growing larger. A few places a new one is popping up, but for the most part, it's those crystals that nucleated at early times that are just continuing to grow. And so that really begs the question of what determines this initial behavior during this initial period, because that's going to have the biggest influence on the end state. If it's just those existing crystals that already nucleated, they're going to continue to grow. And so in this, I'm going to try to walk you through what I think the answer to that is. So at lower injection flow rates during imbibition, there is more time for the fluid to cool. And so as it flows in, there's a local temperature gradient where the fluid front is cooling, and precipitation begins at that interface at the fluid front. And because precipitation begins, the concentration of the ions in the system starts to decrease. When we compare that to higher imbibition rates, the fluid is moving quickly through the chip, and so it remains hot, and so precipitation doesn't yet begin during this imbibition phase. And looking at the data, this is an experiment that was flowing quite slowly. There's non-uniform front that sort of creeps through, gradually moves through the pore space, and then we can see that sort of mirrored in the precipitation behavior. So this is a fluid front that aligned pretty nicely with some of the crystallization that we see at the end. So just an alignment between sort of the injection scheme and the end state suggests that precipitation has already begun, and that is very crucial to determining the crystallization behavior. Compared to a higher flow rate, the imbibition front moves quickly through the system, sort of spherical flow, just not that sort of wandering path, but more uniform, and it has less influence on the end state behavior, which you see on the right, because cooling during this period is limited, and so crystallization has not begun and doesn't influence the crystallization as much. So in this faster flow rate, what really matters is what comes after imbibition, which is shut-in. So going back to our lower flow rate experiments, in this scenario, they've already cooled a little bit, and they already have precipitated some. And so when we're thinking about driving supersaturation, it's increasing still over this shut-in period. We're still forming more crystals, but the supersaturation is increasing relatively slowly, and so ion diffusion is able to outpace crystal growth, or that reaction rate, which corresponds to a lower Damkohler number. Comparing those to our higher flow rate experiments, they haven't cooled significantly and they haven't precipitated significantly, so these values are still high, and so we're really pulling on that supersaturation lever very quickly and having it sort of shoot up during this shut-in phase. And so in this case, crystal growth outpaces ion diffusion. There's a higher Damkohler number. And what that means is that crystals are not going, or ions that are sort of ready to precipitate are not necessarily going to be able to diffuse to an existing crystal surface before they precipitate because of that really high reaction rate. And so the result of this is that we see more crystals with a higher surface area to volume ratio, which is not what thermodynamics would lead us to expect, and they're more dispersed throughout the system, somewhat more chaotic. So increasing initial flow rate, in blue we have the number of crystals, in orange the surface area to volume ratio, and so in this first slower regime with a lower Damkohler number, we see fewer crystals that are larger compared to at a higher flow rate with higher Damkohler number. There's a bit more chaos, crystallization sort of everywhere and more dispersed. And then just visualizing these from my experiments, we see just a little bit more order at a lower invasion capillary number. Again, crystallization everywhere and much smaller crystals in the higher invasion. And then final sort of case that I'm still working on exploring is advective flow, where we don't have that shut-in period and instead continue to inject fluid throughout the experiment. In this case, crystals grew even larger, and there were fewer of them. And I mean, part of the reason they grow larger is, of course, because we have continuous ion influx. So every time we inject more fluid, the crystals can grow more because there's more ions to precipitate. And then additionally, there is the fact that the injected fluid is hot and keeps the chip from cooling as quickly. And so that, again, sort of similar to our slower flow rate, keeps the supersaturation, the change in supersaturation more gradual. And so similarly, ion transport is able to outpace crystal growth, corresponding to a lower dam Kohler number. So to sort of wrap this up, hopefully synthesize what I've told you about today, we know that crystal growth minimizes a surface area to volume ratio, and that is thermodynamically preferred. But in a system that quickly evolves towards supersaturation, the surface area to volume ratio and dispersion of crystals can be transport limited. And for this case of temperature-dependent solubility, precipitation is a function both of the change in temperature and concentration. So the dam Kohler number is influenced by invasion time and Peclet number. So we're kind of, which corresponds to whether it's shut in or not. So just to start to fill in this regime diagram, at a high dam Kohler number, their cooling-induced decreases in solubility is very fast and outpaces ion diffusion, leading to this really dispersed and small crystals, whereas at a lower dam Kohler number, ion advection diffusion is on par with cooling-induced decrease in solubility, but we can have different sort of like different Peclet number corresponding to somewhat similar behavior. So these two have different setups, but look more similar than these two cases, and particularly this case with that is has the shut-in, crystal nucleation and growth is really influenced by the initial flow conditions. So we know initial conditions are often really crucial, and in this case, it may really be running the show. So with that, just returning to kind of the implications, we could think about the separations process perhaps having an engineered injection scheme in order to prioritize certain kinds of precipitation behaviors in order to have the whatever ideal end state that you're looking for. With that, I want to thank you for your time and attention, and thank my group for all their support with this work, as well as funding sources from Columbia and DOE. Thanks.
Thank you very much, Rosie. Very engaging, clear, and insightful presentation, so thank you for that. I encourage the audience to pose their question in the chat. So we don't have any for the moment, so we'll start with some questions from here, from the studio. I do have one to start with. How do you control or monitor temperature gradients within microfluidic experiments, and what are the challenges you face with that? And can you actually capture them for cooling-induced nucleation at low flow rates?
Yeah, that is a great question and something I think about all the time. So initially, we're not controlling it. We're allowing it to sort of control itself. And it's not something that I have so far had the ability to measure, but now we do have an infrared camera that I'm working on getting set up so we can measure top down. So I think, I'm not sure if you can see my slide anymore. I have like a little image of the cell with...
No, you're not showing a slide anymore, so...
we're working towards having infrared camera to be able to measure temperature. So that's definitely going to be crucial to building our story.
Yeah, definitely. But then you will move from 2D to 2D press time problems in modeling, for instance, if you want to move to the modeling steps. So
Yes.
yeah, interesting. You can do a lot with spatial dimension data for data analysis on this kind of thing. So yeah, looking forward to see the results once you have like this tracking of temperature gradients. And then I would have a question. So you are currently controlling everything on the lab time scale. So how do you see this upscaling to real physical processes? Can you draw conclusion on larger scale models, longer time scales? And if so, what are your insights about this? What would be the main uncertainties? Can you just comment about that?
Sure. I mean, it's really hard. I think, yes, we want to be able to study them on lab time scales, but also it's challenging to upscale them for sure.
Yeah.
I think in this case, the more we can, like, the infrared will help us be a little more quantitative and hopefully translate these results into like dimensionless numbers like Damkohler number that will allow for scaling to some degree. I think also the different crystals have different behaviors, and so this is not necessarily relevant to all types of crystallization, but sort of the more broad idea that the influence of rate of change of supersaturation. I think, if you know your exact application space, it's better to use chemistry that more closely models, but we may be able to sort of get insights from this work that can lead to designing experiments or thinking about how other systems work similarly.
Awesome, thank you. Mehdi, do you have any questions for Rosalie?
Yeah, I actually have. How did you come up with the system of 3D printing and glass beads? Like, is there any specific reasons why you didn't choose like traditional microfluidic systems?
Basically because these are a lot easier to fabricate. So we have a 3D printer in the lab. These probably take me, I don't know, maybe half a day to make a chip. And because we're precipitating, first of all, a lot of these clog. I probably did, I don't know, 2 or 3 times more experiments than I'm able to use. And with traditional microfluidics, that can be sort of horrifying to lose weeks and weeks of your time. And so because we're fouling them, we're totally just basically they're entirely single use, maybe not even one use. That was the reason why we chose this approach. It's a little more, I don't know, coarse, I guess. They're not super polished and exactly the same as each other, but we're just able to make them so much faster and allow for a lot more experiments.
Nice. The last question would be like, what do you think, like if you put your system in a thermal bath and so then you can control the temperature, what do you think is going to happen?
I mean, I think if you had the ability to control the temperature, you would be able to control the precipitation. I think that would, like, if you cooled it more gradually, you would be able to sort of optimize for growing larger crystals. If that was desirable, I think you could also, there's obviously a fair bit of non-uniformity in the system as we just allow it to cool ambiently. It might be a bit more, uniform throughout if the cooling was entirely even all over the chip.
Thank you very much. Thank you.
Thanks for the questions.
I don't see any question from the audience online, so yeah, feel free to contact Rosalie if you want to collaborate with her, or if you have like later questions and you're seeing this on a different time. So I guess we can move to our second speaker.
Yeah, David. So for our second speaker, we have David here with us in the studio. He's a postdoctoral fellow in the group of multiscale operations in porous systems in the Department of Mechanical Engineering in Eindhoven University of Technology. Here, he's investigating how flowing porous substrates can be used in the transition toward the renewable industry. As a part of his research, he's investigating model approaches for port application level and aim to provide fast and easy to use solutions which offer the best trade-off between complexity and reliability. His main research interest focuses on reactive multiphase flow as they appear in chemical reactors, heat batteries, and fuel cells. Yeah, the floor is yours, David.
Well, now my mic is there. Super nice. Thank you very much for the introduction. I hope the technical issues from my side are now resolved. Otherwise, I'm very sorry. Yes, so I'm much more into the chemical processing, right? So and there I'm looking more into evaporation and precipitation. So there's a very nice connection with what Rosalie just presented. I know we have to have a lot of people more from geosciences, so I will start with a, if it also, yeah. What I will start with introduction, what I call the banana issue. So here on the right side, we see a wonderful, huge banana plant with my wife for scale by the side. The problem is this is not somewhere in Colombia or so. It's in the backyard of my grandfather, who lives in Germany, right? And that's if you wanted to have a nice picture that summarizes change, I think that summarizes it up. And we even had last year, we had the first fruits. So we actually harvested bananas. Not tasty, but we had bananas. The effect counts. Now, of course, there are many ways how we can treat this, and the one that I am mostly interested in is really the sustainable feedstocks, energy transition, feedstock transition, where we talk about things that we have to adapt our current infrastructure. We have to find new products. We have to find ways how to produce those new products. Yeah, and we have to maybe establish new processes, either adapt old ones or make new processes to find out what is happening there. Now, if we look at the typical production process, this is what you usually have, like a production plant, huge towers with some kind of porous materials inside, so catalysts, supported catalysts most of the times. And if in the session 59, I believe, my colleague Ali Fatiganielu also had a nice presentation where he does pore network modeling on this kind of reactor scale to see how that happens dynamically in such a system. But of course, we talk here. I am not some. I am also interested in the reactors, but I'm also more interested in what happens inside those catalysts, where we have usually in some cases we have gas fluidic flow. We have a solid phase that is in there. We have a reactor. Heat is produced. We have mass transfer limitations, heat transfer limitations, and all of this caused by what is happening at the surface of those grains, really inside a pore, nanometer scale. Now, I'm mostly interested in those catalysts. So how can we produce them, and how do they perform best? And there are a few side conditions we need to think about. So if we are in a production, we have, let's say we have a spherical particle, there's a lot of catalysts inside that we want to use. We have the first problem, catalysts are extremely expensive. I mean, if we talk about nickel, that's a cheap one, and that's already not considered usually very cheap for manufacturing. We can go to ruthenium, gold, what you want, usually expensive. You don't want to waste any of those. When you are now in such a production process, so inside your reactor, you also talk a lot about heat and mass transfer resistances. That's fine, right? So we have some kind of the heat has to travel in, it is consumed in the reaction, and the educt has to go in, the product has to go out. They're all competing, tricky. Additionally, in such reactors, if it's a solid packed bed, yeah, attrition is often not much of a problem, but it can be if you talk about fluidized beds, like the fluidized cracking systems. They're constantly colliding and things are chipping off, which is also not necessarily good for your for predicting what is happening there. And finally, we have poisoning. I mean, it's all nice if your educts are pure, but in reality, they never are pure. So we have problems with poisoning. And that all of that leads to the result that what is practically done, we do not practically we do not homogenize the concentration of the catalyst in our particle. We try to have a dedicated profile inside. Right, so if it chips off, we don't lose any of our valuable catalyst. We don't want to have catalyst at a place where it's reached. This kind of problems that we are investigating. And now during my PhD, I mean, I was a bit. I looked into the production of those. So how can we control that those that we get also the profile that we need theoretically? And for that, I looked at the most common process to produce those catalysts. That is usually called the incipient wetness method, where you start with your dry porous material with a very high surface area, wonderful theoretically. Put some liquid inside, so you impregnate it with a salt solution, wonderfully with your the expensive catalyst dissolved in there. Then you dry it, so heat it up, want to get rid of all the liquid so that only the catalyst is left over. And finally, you calcinate it so to refresh the surface of this catalyst. Now, if you're a bit into catalyst production, you will see, you will usually start thinking about impregnation if you want to think about the profiles. Often those impregnation is not relevant here because we're talking about high loads. So we have usually industrial catalysts try to go up to 48% of catalyst on a support. Then impregnation, the adsorption on your surface that it's happening during impregnation is irrelevant. What is really relevant is the drying step, where the liquid goes off, the crystals are forming, and also the capillary suction redistributes everything inside your catalyst. And one thing that I was then starting to investigate in my PhD. Now, first we have to look at what are the transport phenomena inside such a catalyst pellet. And if we look at it from a very schematic point of view, we have a liquid phase, we have a gas phase, we have something dissolved inside our liquid phase. And if we now evaporate, we form here at this point contact angles or contact lines. Those contact lines lead to capillary. So our liquid is moved towards the gas phase because it wants to counteract those what is happening there. Additionally, we have evaporation, which means we have a cooling locally. So your liquid is cooling down. That has to be somehow transported by heat transfer. We have an air and vapor flow, right? So we evaporating something, that vapor has to leave. And eventually also maybe inert gas has to go inside because we don't have any vapor anymore. And finally, we have, of course, oversaturation and precipitation inside. There are, of course, more effects. I mean, we also, Rosalie already mentioned ions. So ionic transport is actually one of the classic ways to control your the movement of your particles inside. You have very large molecules that you attach to your salts, counter ions, and they will drag the whole material, so it won't be too mobile anymore, for example. I'm ignoring that for now, just for the reasons. And also there are more advanced, very advanced ways how we can model adsorption. I'm also being very simplified, doing this very simple. If it's across the saturation limit, it precipitates. I don't think about adsorption further on. Sounds very simple. If we put that into equations, it looks horrible. Usually I make this slide to scare people a bit, so I can establish that this is also very valuable what I'm doing. But in the end, it's a quite simple thing. We have 5 phenomena we have to look into. One is the water transport. Second is the air transport. We have the heat transport, of course. And those have been established in a numerical frame or in a model by Vue and Sotzers in Darmstadt, I believe. And finally, I added a bit of salt transport and precipitation to it. So those 2 equations. And now we have to solve them together. The most important part here, so before you completely shut off because there's so many equations, the only thing I really want to highlight here, this is a phenomenological model, which means we have a Darcy type of flow So we have a very phenomenological approach, very effective coefficients, but you also see here with an effective diffusion coefficient, effective heat transfer coefficient, and in the end, does sees also an effective velocity. I do not read the pore space at all. This is all inside our effective parameters. And with that, I hope most of the scary equations are gone. So now, before we can look into the results, we first need to understand a bit how does drying of such a porous material actually look like usually. And if we look at it without any salts, so no interaction, nothing at all, there are you have here, this is a very classic way how to look at it. We have the moisture content over a drying rate. And we see we have for a long time at high moisture contents, we have a constant drying rate period. And at one point, this constant drying rate period stops, and we have a falling drying rate period inside our system. And this is usually the point where it happens that we have the liquid cannot be transported to the surface anymore. This one here, the constant drying rate period, is supported by capillary suction towards the surface. So there, it's simply like the surface is always wet. And it's evaporating constantly. But at one point, the capillary suction cannot sustain this anymore. So it will withdraw within our support, and that is when the falling drying rate comes into play. And to make sure that this model that I implemented also works, we have here some validation data to show you a bit the whole process from the fully saturated, where we go then the long constant drying rate period and go to the falling drying rate period. Interesting also from a temperature point of view, if you do it at room temperature, the temperature inside your pilot will fall, right? Adiabatic drying temperature here, somewhere around 30 degrees in the center for this special example. Okay, now we've seen a bit how it should look like, those kind of systems. Let's look at what people usually think about when they talk about drying of catalysts. And often what you will see is a drying front. This is the classic model that says, okay, we just have basically like a droplet, and the droplet is shrinking, and the porous medium is just a way to get effective coefficients out of there. Very popular, very wrong. There's a wonderful paper by Schlüter from 2004, who did a lot of work on the drying, on this receding drying front models, and where he basically says, last 30 years of my research, I realized this doesn't make sense physically. Doesn't mean the models do not work within certain limits. I will also show you that, but they are not necessarily physical because they basically neglect capillary suction. That's the basics idea behind it. Now, if we do a full this simulation that I showed you with the capillary suction, and we do that with different viscosities, we have here the radius of our spherical particle, let's say it's 4 millimeters in diameter, and we have the saturation levels, and we start at 0.001 Pascal seconds. So this is basically water. What you will see here is that actually almost all the water is transferred to the surface until we have here some kind of snap-off area. This is when the liquid is not in the bulk anymore, but only is the leftover at the surface of the inner surface. So there is no bulk anymore, no capillary suction, nothing anymore. This is when this kind of problem happens, but then we also don't have transport anymore. So if we have water, there's actually no such thing as a drying front, except once we have no transport anymore of liquid. Now, if we increase the viscosity, what is the possibility in drying? We try to get the liquid in, and we try to increase viscosity to prevent that we have subcapillary suction or reduce the impact of it. You will see that, okay, things become more and more like we expect this drying front to look like. So we have from 0.01, so 10 millipascal seconds, 100 millipascal seconds, and 1000 millipascal seconds. To give you a bit of a reference, because not everybody is good with those values, right? This is about a bit more dense, more viscous than yogurt, right? This is going to move a lot in a particle with a pore size of 10 nanometers. It's not going to move a lot. And then we actually see this kind of drying front appearing again. That also explains partially partially, why some of those receding drying front models worked for a long time and why it was not immediately clear that they are physically wrong. Just mentioning it here. This is because those models have their relevance, not strictly speaking, but there's not strictly speaking physically correct from what we know now. Now, let's have a bit of a look at another property, that is the gas pressure inside. That's a bit of an interesting one. Because I mean, you would estimate, okay, we have evaporation, so we are limited by temperature and what the pressure looks like. But in the end, we have to be clear that there's also inert gas inside that has to go out. So we try, and there's also the liquid levels are falling. That has to be substituted by a lot of inert gas going in, for example, air or nitrogen. And eventually, when everything heats up, and that has to go out again. And what we see here, this is the gas pressure over the radius and how it develops, or the pressure profile over certain time steps, and also the liquid saturation, but mostly the pressure is interesting. We see that we have a very high pressure at the center of our particle. And we talk here about a 4 millimeter diameter particle, which means we have a huge pressure gradient, which in the end leads to huge stresses on our catalyst, which in end effect leads to the breaking of the particle. So this is a bit of a quality management part. If we can reduce the pressure inside, we can also prevent the breaking of the particles during the drying process. And we get more healthy particles, which we can then finally use in our reactor. Now, there's of course the question, what happens if you have varying liquid viscosity? What if this viscosity depends on your concentration? Usually we would say if depending on the salts you have or other additions, you might glycerol or so, you go to a very high, you'd reduce the water, glycerol does not evaporate, and then suddenly at one point your viscosity jumps up. I will not talk about this here in view of time because I want to still show you something else, but I will just show you for the one of the papers that we made out of this model, which also has a bit of a nice trick on how you can control profiles with just by managing process conditions. But now the next step, because we're also talking more about subsurface, right? A lot of people that go into subsurface modeling. There's something else I was interested in. That's the morphology of the pore space. So how does our pore space have an impact on the redistribution in our particles and in our process on the evaporation and precipitation? And I mean, there are a lot of parameters we can have a look into. That is, of course, you have porosity, we have a specific area, we have a pore size distribution, all of those wonderful properties we can think about. And how somehow we have to get out of those ideas about our permeabilities, right? Talk about the sea flow, we need a permeability. We need to have an idea about how our diffusion looks like, how does our conduction look like. And finally, what most people probably are familiar with is the saturation capillary pressure curve. And there are many different ways how you can describe such saturation capillary pressure curves, right? But I wanted to know what happens if I change my pore space. So which means I need to have some kind of description that allows me to take for example, a pore size distribution and get a saturation capillary pressure curve out of there. Yeah, it's really like a parametric investigation. That's why in the end, what I chose was a bundle of capillary system. Not very realistic. Okay. But it has the advantage that I can take any pore size distribution and I get my permeability values back. I get my partial permeability values back. And even most important, I get my capillary pressure saturation curve back out of this adaptation. And then I can do a very nice parametric investigation. For example, by saying, okay, I change the volumes between my different modes in the pore size distribution. Now, to give you a bit of an example, I looked in catalysts. So we talk about usually 10 nanometer size pores. Yeah, can even be smaller. And I now more or less arbitrarily I said I have a 1 micrometer pore, somewhere, a peak around there, right? There can be fractures that can be designed in there. And just saw I looked what happens if you have to your permeability and to your the filling radius. It's usually and with permeability, what you might expect, of course, if you have like let's say if you have 50% of your volume is in the large pores, yeah, we can get actually quite large liquid permeabilities or gas permeabilities in our system, right? If we have large pores, we have lower resistance, and we get a lot of flow that can go through there. And if we reduce the amounts, we go 40, 30, 20, and we go further down in those pores, of course, the permeability decreases. And we see more and more of the permeability actually going towards the lower levels, where we in this graph actually cannot see it anymore, to the point where if we have 0 large pores and everything is 10 nanometer pores, we don't even see it in this graph anymore. So there's a bit of a, I hope I give you a bit of an idea what is happening there. But let's have a look at the final results, what it looks like. Now, I'm looking into 2 things. I already mentioned the pressure. That's a bit of a tricky part to look into and to estimate. But what we now basically see here, this is the pressure at the center of our particle over time. And we see at 0% of large pores, so there's only small pores. In this system, we get a very high pressure drop. We talk about 5 bar over 2 millimeters. It's a bit excessive, right? It's a bit of the, because I use the high viscosity, the effect a bit more in clear, but it's there in every for every viscosity. We see how we have a very high pressure drop, but only if we have 0.01% in large pores of this large pores, already our permeability, our pressure spike goes down a little bit, and even further down if we have 0.1% or 1% in very large pores, the pressure drop we get over our system is extremely drastically. But of course, that's a bit of a quality management problem, so that we want to have less cracking. But of course, we want to know, is there a downside? I mean, how does the profile that I get finally in my catalyst, does this also change? And how does it change if I have those large pores, either by cracking or by design? And that's why we look here into the surface load. I'm a bit sorry about the quality of this image. I don't know what happened here. Usually it should be better. But what we see here is the load, so that's in the kilogram per kilogram over the radius. And especially for the first few, where we have only a little bit of the very small pore, very large pores, a little bit of the very large pores, we see here that the profile barely changes at all. And this is exactly the range until the pressure drop does not have any, the pressure drop, the pressure spike reduces a lot. Until we have here around 5%. Let's say 5%, engineering point of view, I would say this is still okay. And this is, we don't even see that here on the graph anymore in the pressure peak that it produces, which basically leads us to the conclusion that it might be possible to either design one of those supports in beforehand, and to give it basically those extra pathways so the gas can go out without disturbing the liquid transport and without building this high pressure drop, which then would crack our particles. As an idea what we can read out of this. So with that brings me already a bit to the conclusion. So when the whole thing is dry, and what have we learned? So this is now a phenomenological drying model, right? So it's very rough. It gives you an idea about what is happening there. It's using an analytical pore space model, this capillary of tubes model, which you can dispute. In the end, what this research also showed a bit is that with the smart support design and the process design, this is the one that I kind of skipped over because I referred you to the paper, that also smart process design can help you improve the control of how you distribute this precipitation inside your catalyst. But of course, there are always, I mean, this is a very parametric system, a parametric model, a bundle of tubes. I mean, I get weird looks if I present this with geoscientists. It's not the best model, but it was the only one I could find that really gives me what I need in a nice and consistent fashion. Yeah, percolation is not modeled at all. So that you have snap-offs of isolated pockets in there that then the liquid does not move anymore and just dries shut in there. We get large crystals, which we actually don't want. We want to have a small surface area, a very large surface area, very small particles inside our catalyst. The pore space is actually shrinking throughout the process. I mean, we talk here about 10 to 40% weight percent of material in there. This is not negligible anymore, but everybody conveniently does. Interesting. Huh? Yeah, multiple components. I already mentioned that. So ion transport is not a trivial thing. Also, implementation-wise, it's not completely. And then the interpreting the results that you get is also not completely trivial, but it's doable. We should definitely investigate it. And of course, one of the other questions is also, aren't those pores super small? I mean, we talked here about 10 nanometer pores. We're talking about things like Kelvin effect coming into play. We talk about where the limits of our models, the model limitations. We are not, or we're barely in a continuum anymore. And if you look at what people can do in this kind of really poor resolved simulations, you see that this is not a clear, or we have the evaporation is actually taking place in a wider area than just in a very sharp front, as this is now in this model kind of working out. And with that, those questions, I will, hope that you've learned something. If you are in Interpore, you can always Interpore is coming up soon. And also, I didn't mention it here, but all of this, the model and the papers come with the code, the MATLAB code, which models this. So if you're interested in repeating this, or doing something more on it, feel free to contact me. I can point you to the right places, and I hope it's clearly enough written that you don't even need me to work with it. And with that, thanks.
Thank you very much, David. Very engaging talk. So we have some question from Marshall in the comments. First of all, fantastic work, David. Congratulations. Marshall asked, was there any special reason for using bimodal distribution? Are they more common in the practical systems?
Yeah, thank you very much for the praise. So bimodal is mostly the idea that I wanted to have something to get the idea what happens if we have a non-conventional type of pore space, right? We could think, I mean, fractures usually have their own trickiness in there, but I mean, this was one of the things I thought about there. Also, it's more of the question exploring what can we do. So with the in this kind of, if we can do it by design, I mean, there are people who design such pore spaces with those bimodal distributions. And in the end, I mean, I also did a PhD, right? You need to get to something. And this was a very convenient way to get some interesting results and to, let's say, trigger a bit all those people who do catalyst synthesis, to give them some ideas what they still can do. I hope that answers the question, or otherwise, still elaborate on it.
Okay, thank you very much. Is there any question in the studio? Sarah, Rosalie?
Yeah, I do have a question actually. So you were talking a lot about parametric investigation for the impact of post-peri morphology, but I was wondering on your mathematical model, you have effective parameters that comes from pore-scale dynamics, right? So my question is, how do you calibrate these parameters for your modeling and experiments, and what are the main uncertainties associated with such a calibration in your case?
I mean, that's a very good question. Let's go back a bit to the model, right? Especially this one here, the bundle of tubes, right? Honestly, this is not. I do not calibrate the model. I do not intend to target. Or I did not intend. Or I did not calculate. I intended to. But then Corona came in between, and our labs were closed. So in view of time of my project, we decided I'm gonna go fully numerical, right? But if we talk about, let's say, practical application, I mean, a very easy way would be to just take this model, and make a fit factor to it. Take the maximum permeability, what happens, or I'd say, and compare that with what you get from your material. one of the things. One of the options I also discussed was adding something like a tortuosity factor,
Yeah.
right? That's something you could probably calibrate. How realistic it is up to debate. But yeah, that's also a bit the one thing I'm a bit still, or let's say what keeps me now going, this kind of model. I mean, I would like to have such an analytical model that I can also easily calibrate, right? But it gives me, it reflects the geometry properly. But most of the models are actually, almost all models of those capillary saturation, capillary pressure curves, they are more defined for a certain system, or they have this fractional factor or so in there. I don't find this very satisfying, because it usually refers to a single type of pore space, or to to some kind of fit factor that I cannot really make my mind up what it's supposed to be. Yeah?
Yeah.
And that's a bit where I am now going also with my new group, and also further research is in how can we make this more reliable.
Yeah.
Right, and how can we reflect pore spaces? What are the factors that we need? What are the actual influencing factors that we need for calibrating such a model?
Yeah, and this is where uncertainty also can come and play a great role here in such calibration. Right? If
Yeah.
you want to enhance reliability, then you move towards
Yeah,
quantifying how reliable you are.
I mean,
Okay.
I also have to say that this catalyst community,
Yeah.
or at least those who produce catalysts, are extremely close knitted, because this is a bit like black magic, right?
Yeah.
So they're not going to share their recipes with you, because this is
Okay.
what the companies make money. Yeah. So they're not going to just let you have any recipe to play around with. So for them, it's a lot more valuable if you give them like some indicators, which knobs they have to turn to get a better result.
Nice.
And they don't have to share anything with you.
Yeah.
Right.
Uh,
All right. Okay. Yeah, I think Marcel has another comment. So just out of curiosity, do you know of any attempts to include the snap-off effect in the bundle of models make things a lot more convenient analytically, as you mentioned?
I mean, there are other. So in the bundle of capillary models, I'm not aware of. It depends a bit also on the model that is behind it. I mean, because for example, this model by Vue and Tsotsas that I used already has this snap-off part, right, where we say, okay, everything is adsorbed to the surface, and then it's drying there without moving. Yeah, and that interferes a bit with the snap-off part. There have been other approaches. There's especially the group of Benjamin Glasser, so in Rutgers University, has worked also in the 2000s and 2010, early 2010s, on catalyst preparation models, and they have included percolation. And I have also, just out of curiosity, just added some kind of simple percolation factor in this model. I did not see too much difference, because everything in this model that I use now basically has to do with this adsorption to the surface. I did not see too much. But of course, it would be super interesting to get something like this going, although this maybe with another type of model, because this bundle of capillary model is it's super simple to start with, but it also runs very early into limitations, because we talk about a very sharp drying interface. So this very one radius that we are talking about, and if that rate, and otherwise you have to spread maybe this radius to get a sphere of influence or so. Yeah, or we start completely directly with how's it called, population balances for the pore size distribution, which I started kinda, but it was also in the 4th year of my PhD, and due to time issues, I stopped again.
Okay, thank you very much. Sarah and I, on behalf of the Porous Media Tea Time Talk, appreciate your talk, sharing your presentation with us, and also appreciate people who joined us for these presentations. For the next month, we would have at the 10th of June 2 amazing presentations. Please note them in your calendar and join us. If you want to collaborate with the speakers, please write an mail. And if you have any comments for us, also write a mail to us. Thank you again. And I wish you a very good morning and afternoon for people all over the world. Bye.
Bye, Ram.